All right, so here we go at the last page. So remember from in class today, if something is onto, it means there must be at least one solution. So that means like one solution or infinite solutions. To designate something as one-to-one, it needs to be one solution or no solution. So because in a sense, no solution is a single solution. It's that there is no solution or whatever. So it can't be anything like infinite solutions. All right, so we need to take this transformation and see what's going on. So to do that, we are going to build a matrix. So I have to do everything. Basically, it's given to me a little bit different than before, but I have to make a matrix and I have to say, hey, what are the changes to x1? So if I look here, x1 is staying x1 in this problem, and x1 doesn't exist over here, so there's a 0. x2, so my second column, is -5, and x2 over here, it has a 1 in front. So really we're kind of going like across in a way. Over here, x3 has a 4, and x3 down here has a -6. Okay, so if these were my coefficients, so it wouldn't really matter like what my answers were over here, because what I see here is that there is going to be a free variable, and that free variable indicates that there's more than one solution. So this is infinite solutions. Therefore, I cannot be one-to-one. But I am onto. Okay. All right. And now I see this is a little bit out of focus. Sorry about that. All right. So this guy here. So you have a transformation from R2 to R3. So recognize that you are going from a 2-dimension to a 3-dimension. So your transformation right here is going to be, oops, I drew that a little bit too short. So x1s go down the first column. So I got 1, -1, 3. And then I have -2 for x2, and then 3, and then -2. So that's a little bit harder way to look at it. But another way to do it is just be like, oh, 1, -2, that's the row. -1, 3, that's the row. 3, -2, that's the row. So this is my transformation matrix. And I want to find an x such that when I transform x, it becomes this, -1, 4, 9. So let's practice a little bit of reading through or figuring out the sizes. So this is a 3 by 2. I want to multiply it by something and get a 3 by 1. So I know this has to be a 2 because these need to cancel or like match up. And so 3 by 1 is my ending size, so is a 1. So it's a 2 by 1. All right. So let's go ahead and do it. We put our stuff, 1, -1, 3, -2, 3, -2. Augment it with my answer here, -1, 4, 9. All right. And I will ref it. Sorry, I am going backwards here. So when I ref it, I get 1, 0, 0, 0, 1, 0. And 5, 3, 0. So actually, I get a nice, easy answer. And since it came from a smaller thing, it's okay that this is just 5, 3. Because remember, I want a 2 by 1 matrix. So my x is the vector or matrix 5, 3. Okay. So if I put 5, 3 right here, when you do the multiplication, you come out to this guy right there. That's why knowing the size is important. So putting 5, 3, 0 would not be correct. Right. So in Theorem 11 it says if you have a linear transformation, then t is 1-to-1. If and only if, when you have a homogeneous system of equations, it has only the trivial solution. So remember this. This is like a word game here. 1-to-1 means this. It means one solution or no solution. Now remember, when you have a homogeneous system or a homogeneous situation, it always has a trivial solution. So always has a solution of, 0. Always, 0, 0, 0 is the solution, or however many you need. There's always the trivial solution. So that has to count as your one solution. Okay. That's it. I guess it could have no solution also, but this always has a trivial solution, so it can't have no solution. So that's the only way it's going to be. All right. This next theorem 12. So your transformation maps Rn onto Rm if and only if the columns of A span Rm. So that just means, to span something means it's a linear combination of those things. All right, T is 1 to 1 if and only if the columns are linearly independent. All right, because remember, linearly independent means not a multiple of each other, and so you can't have infinite solutions because then your columns are multiples of each other, and you don't want that. All right, so here we go. Is a standard matrix here 1 to 1 on to justify our answers. So I took this here. I did put some 0, 0 there if we didn't really need to, but just to imagine like this last little theorem here. But anyway, this reduces down or refs down to this guy here. So when I look at that, I have a free variable, so it means I have infinite solutions, which means I can not be 1 to 1, but onto yes. So it also means I have something besides the trivial solution. So that's another reason why I can't be 1 to 1. All right, this guy down here, it RFs into that. So T is a linear transformation whose standard matrix is given. Does the transformation map R5 onto R5? Now remember, to be in R5, you have to have 5 pivots. So let's count them up. 1, 2, 3, 4. Oops, not a pivot. No pivot there. So it only maps it onto R4. So my answer to this would be no, it does not. It maps it onto R4, not R5. And that is it. I'll see you next time. So remember on your homework to do at least like 3 or so problems, maybe 4 if you have time. All right, bye-bye.